Hello, this is Dr. Liu. In a previous video, I explained how to do differential calculus, the very basic. Mostly I was focused on the differentiation of polynomials. So now I have a couple of questions in physics, introductory physics, to use as examples that would require differential calculus in order to get answers. So let's take a look at the first one. This one is from University Physics, Chapter 3, question 36. It was labeled as an unreasonable answer question, which means the answer may not be reasonable. So let's take a look at it anyway. In this question, we have a particle. It moves along the x-axis according to this expression. So the position as a function of time, it depends on the cube of time and also time linear. So there are some factors. So 3t cubes plus 5t. That's how position depends on t. And the question, at what time is the velocity of the particle equal to 0? And is it reasonable? So let's do some reviews first. First of all, what was the, let me just change the color. So the formula for differentiating a polynomial. So here we have a polynomial y of x, the same as x of t. And that is equal to a factor a times x to the nth power, and the dy over dx is equal to a, and the n drops out as another factor, and x to the n minus 1 power. Alright, so we have this. We can also, just for our convenience, write this as dx over dt, so that is equal to a n t to the n minus 1 power, because t is the independent variable here. And we were asked about velocity. So how do we get velocity? Well, in one previous video, I indicated that velocity and position, they're related by differential calculus. So let's write that out. So v, let's move it down. V is equal to dx over dt. Right, so that's the definition of instantaneous velocity. You have to take a limit. This is also the limit of delta x finite x delta t finite t when t delta t approaches 0. So that's our differentiation. Essentially, we are saying that dx over dt, or x derivative with respect to t, is velocity. So let's get velocity then, just by differentiating. So we'll do dx over dt to get our velocity. So d over dt, because we have two terms, each term can be differentiated separately, and then the results added. D over dt, that's the differentiation, 5t. Okay, so let's practice the differentiation rule of this polynomial. So a here, the factor is 3. And then the power of x drops out. That's also 3. So 3 times 3. And then 3 is decremented by 1, so we get a 2, t squared. And then plus 5, that's a factor. And this is t to the first power. 1 drops out. We can say, well, it doesn't drop out. It doesn't matter. And then t to the 0th power, so that is a 1. So that is just a 5. So this is giving us the velocity, 9t squared plus 5. So this is the velocity as a function of time. And you can also find the acceleration as a function of time, but that's okay. We were asked about the velocity, so let's see if we can get the answer. So we were told to find the time t when the velocity is 0. So okay, that means velocity equals 0. That is 9t squared plus 5 is equal to 0. Okay, so is that reasonable? Well, let's see. Well, we have t squared equals negative 5 over 9. Okay, so t would be equal to, well, plus minus the square root of a negative quantity. Well, is it reasonable? I guess it is not reasonable, because, well, t cannot be imaginary numbers. As much as I like imaginary numbers and complex numbers as an extension of just real numbers, time cannot be imaginary. So it's imaginary, and that's why it's unreasonable. But this doesn't really mean that we cannot do the differentiation. It just means, yeah, we did the differentiation. It's just the values there somehow caused the t to not be a real number. So that is just how the problem is set up. Okay, so we did our practice with differential calculus. Let's do another problem that does give us reasonable result. So here's the second question. I'm going to move it up so I can get some extra space here to write the steps down. This is another problem from the OpenStax University Physics textbook, Chapter 3, question 113. The position of a particle, well, another particle, moving along the x-axis varies with the time according to this expression, x of t is equal to 5t squared minus 4t cubed in meters. And we want to find a number of things. First, we want to find the velocity and acceleration of the particle as functions of time. So we know how to get velocity as a function of time. We differentiate position, and then to differentiate velocity, we can get acceleration as a function of time. So let's go ahead and do that. So velocity as a function of time is the position as a function of time. I'm just reminding the audience the position is a function of time, or dt. So that's d over dt. This whole expression, 5t squared minus 4t cubed. So we already know how to do that. We can separately differentiate these two terms and combine the results. So let's just do that in our heads now, because we have done examples, plenty of examples. So we'll just do 5, okay, and the power 2 drops out, and the power decrements to 1, so that's just a t, minus 4, power is 3, then t cubed becomes t squared. So this is 10t minus 12t squared. So that's in meters per second. Since it was stating the unit, it doesn't hurt to have the unit. Just clarify that. And acceleration as a function of time is the velocity over dt. Rate of change of velocity is acceleration. So that's d over dt, 10t minus 12t squared. Okay, so this is just another differentiation. Each time we're getting lower powers of t because the differentiation drops powers of these polynomials by 1 each time. So let's differentiate in our heads. So 10t becomes 10. The t's first power drops out of 1. Okay, remember that now. And then t's zeroth power is 1. Okay, so then minus 12, and then 2 drops out with the 12. 2 is 24, and then t squared becomes t. So that's the expression of the acceleration with meters per second squared. So we answered part A. Alright, so let's look at part B. The velocity and acceleration at time equals to 2.0 seconds. Okay, since we already have the expressions, we can plug in t equal to 2 and find the velocity and the acceleration at that time. So let's use the space on the right side. So velocity at 2 seconds is equal to 10 times 2 minus 12 times 2 squared. So 10 times 2, 20. 12 times 4 is minus 48, and plus 20 is minus 28 meters per second. Okay, so acceleration A at time equal to 2, we have 10 minus 24 times 2, that's 48, and with a 10 minus 38 meters per second squared. Okay, so that answers part B. And the velocity and acceleration at these times, well, at this particular time. And part C is asking the time at which the position is a maximum. So when is the position the maximum? If you look at this expression, you have to think about it. Maybe I should use that equation plotter just to plot it out and see where the maximum is, right? Maybe there's another way. What if I can't really plot it out, or maybe not accurately? So how do we determine a maximum, or more generically, an extreme? So in this example, we can think about this as when the position is maximum, that means, well, the velocity is going to be 0. It has to turn around and go backward in order for it to be at the maximum, right? So in this case, we can use the physics context to say that the maximum velocity must be paired with a 0 maximum position is paired with a 0 velocity, because you need to turn around. If you don't turn around, then you keep going, there may be another new maximum further down in time, right? So the maximum position, so x max, I require the velocity equals 0. Okay, so that's one possibility, and let's go ahead and do that. Velocity equals 0, and that's the expression. This whole thing equals 0, and we solve for time at which time the velocity is equal to 0. So here we can factor out the t, and 10 minus 12t. So this product is equal to 0. That means either term could be 0. So we solve this simple quadratic equation. T is equal to 0. When t is equal to 0, the product is 0. Or t is equal to, this whole thing is equal to 0. Then t has to be equal to 10 over 12. And you can write it down as 0.83 if you want. So that is 0.83. Just keeping 2 sig figs in seconds. Okay, so we have 2 points in time when the velocity is 0. So it makes sense just to check which one has a higher amount of position, right? We can just take the t, plug the t into the position expression, and see where the x is at time 0, at time 0.83, just to see where the position is, and the larger one must be the maximum. So that, think about that in the physics concept. That's what we can do. So x at the time equals 0, that's pretty simple. This is 0, that's 0. So that's equal to 0 meters. And x at time equal to 0.83 is equal to, now we'll use Python. So let me move Python over. I'll put it on the right side. This one could go to the left side. Okay, so here's my Python. So what I need to do is to calculate here this expression, right, when t is equal to 0.83. So let's say t is equal to 10 over 12 to maintain some high accuracy. And then we'll calculate 5 times t squared. So the double, the multiply, that means to raise to a power of 2. And minus 4 t cubed. Okay, so this gives us 1.16. Or maybe 1.2. It depends on how many sig figs we're keeping. If we're looking at the question has 2 sig figs. We should probably keep 2 sig figs. So let's actually do that, and we'll go over here. It's not really moving. So this x is 1. Okay. 1.116, approximately equal to 1.2 meters. So apparently this is the time at which the position is maximum, because this other time is not. Okay, looks like my stroke was actually interpreted as being here. So with that dot, yes, the program could use some improvements. Okay, so this is using the physics context to understand how to do this problem. Okay, let's keep doing and doing the problem. Part D, the time at which the velocity is 0. So we determine it must be this time, not that time. And the maximum position, we have determined it to be roughly 1.2 meters. Okay, so right here I could say, well, yeah, we finished the question. This is good enough already. But if you know a little more about differential calculus, you can actually use just the math concept to say that, okay, in order for us to determine the maximum value of this function, to find max of a function, let's just say f of x. Here's what we did. We went for not the function itself, x, but we went for its derivative and set that equal to 0. So we can generalize that idea in math. If you want to find the maximum of a function, first you differentiate this function with respect to its independent variable and set that equal to 0. Okay, so what this gives you is, it gives you another equation. You can solve for the independent variable. You could get a number of roots depending on the highest power of polynomial in the differentiation. So in our case, the differentiation of x with respect to time is velocity. So it has this quadratic term, so second power. That's why we end up with two solutions. And then we must check, right? We must check which one is the maximum. So here's where we can actually do it this way. And when we solve it, and the differentiation equal to 0, you can graphically imagine that as a horizontal trend line. So the horizontal trend line, this could go different ways. For example, if you have such a curve and a horizontal trend, not trend line, tangent line here, 0 slope, that gives you maximum. But you could also have something that goes like this. So minimum also gets picked up the same way because that gives you a 0 derivative. Or it could even be something like this, an inflection point where there's neither minimum nor maximum. It's just that the slope goes through 0, right? So we could have all these three possibilities. We have to knock out the minimum and also inflection point. So how do we do that? We do this. We take a second derivative. And then we plug in the value, x. So if the second derivative well, we want maximum, so less than 0, equal to 0, greater than 0. So less than 0 will actually get max, equal to 0, we get inflection point, and greater than 0 we get minimum. So you can try this. I don't really want to go through this. This is a bit off topic, but you can try this. You can try the acceleration because you already have that. Acceleration is the second derivative of position with respect to time. So you can take these two, you plug them into the acceleration, see if that's the case. You plug this in there, this is definitely going to get you a negative quantity. So okay, that means this will yield a maximum. And if you plug in the 0 here, it actually yields a 10, so that's greater than 0. So this gets you a minimum. There was no inflection point in this function. So this gives you the mathematical version of how to solve an extremum problem is to take a derivative, set that to equal to 0, and you can solve for the independent variable, and it could have multiple roots. And then which root is the one you want? Well, you take a second derivative of that function, you plug in every root. If the second derivative is less, equal, or greater than 0, then you can tell what kind of a position that root is indicating. Is it the maximum, minimum, or inflection point? Thank you.